We usually think of the bladder as, well, just a simple storage tank. But what if I told you it's one of the smartest, most dynamic organs in your entire body? So let's dive into the surprisingly complex engineering behind this personal reservoir. First up, let's just talk about capacity. The average adult bladder can comfortably hold somewhere between 400 and 500 milliliters. Now, to put that in perspective, that's about the size of a pint glass. I mean, for an organ that's usually tucked away in your pelvis, that's a pretty impressive amount of storage, right? And this image, wow, it just perfectly shows you how incredibly elastic it is. See, when it's empty, it's just this little pelvic organ, kind of hiding behind the pubic bone. But as it starts to fill up, it just expands, growing upward, way into the abdomen. This ability to dramatically change its size and shape is absolutely central to how it works. And that right there brings us to the central mystery of the bladder. I mean, how can one single organ be a perfectly sealed, totally secure container 1 minute, and then boom, a powerful, efficient pump the next? It's got to master two jobs that are complete opposites: holding on and letting go. Okay, so to figure that out, let's start with job number one, holding on. We're going to look at the anatomy of storage, all the amazing structures designed to keep everything locked down, sometimes for hours at a time. First off, the bladder isn't just floating around in there. It's held super securely in the pelvis by this whole complex web of ligaments and fascial attachments. That strong connective tissue. If you look at this diagram, you can see how they basically form this support cradle. And that is really our first line of defense against any leaks. Now, if we take a peek inside, the bladder wall itself is just this powerful muscle. And a really key landmark is something called the trigone. You can see that triangular area right there. It's formed right between the two openings where urine comes in from the kidneys and the bladder neck, which is where it eventually goes out. But the real secret to how the bladder works isn't just its shape or its supports. The real power is in its unique layered structure. And to really get that, we need to zoom in. I mean, way in. Okay, so here we are, zoomed all the way into the cellular level. What you're looking at is the bladder's specialized lining. It's called the urothelium, and since it's the innermost layer, it's in direct contact with urine, and trust me, it is an absolute biological marvel. The best way to think about the urothelium is like a high-tech smart fabric. So its outer cells, they're called umbrella cells. They're all puffy and cube-shaped when the bladder's empty. But then, as it fills up, they just stretch out, becoming super thin and flat. And that's what lets the bladder expand like crazy without ever breaking its waterproof seal. So, okay, we've got the perfect container. But how in the world does it know when to hold on and when to let go? Well, that whole control system is run by the brain. And it's really a story of two competing reflexes. All right, so on one side, you've got the storage reflex. Its mission? Super simple. Hold the urine. To make that happen, the bladder muscle has to stay relaxed and the sphincter has to stay clamped shut. This is basically the body's default setting. It's automatic. And then on the other side, you've got the micturition reflex, fancy word for the voiding reflex, which, you guessed it, does the complete opposite. Let's break down the storage part first. If you look at this diagram of the neural circuit, you'll see the main player is way up in the brainstem. It's called the pontine storage center. This thing is sending a constant hold command down the spinal cord through two main routes. One set of nerves, the sympathetic ones, tells the bladder muscle, hey, just chill, stay relaxed. And another nerve, the pudendal nerve, tells the external sphincter, squeeze tight, stay closed. So that's the active hold command in action. Okay, so if hold is the default setting, what does it actually take to flip that switch? Let's get to this second part of our story and see how all of this builds up to a perfectly coordinated release. It really all starts with a signal. As that bladder wall keeps stretching, these specialized sensory nerves inside the wall, they're called alpha-delta fibers, they detect that tension building up. You can think of them like tiny little motion sensors that are sending messages up the spinal cord to the brain, basically saying, hey, we're getting pretty full down here. So that information travels all the way up to the brainstem and it activates the other center, the pontine micturition center, or PMC. You can see it right there next to the storage center. This is basically mission control for letting go. And when you finally consciously decide, okay, now is the time, the PMC kicks off this really complex chain of events that completely overrides that default hold reflex. And the key here, the absolutely crucial part, is the perfect coordination. So like we see here, first, the PMC sends the go signal. This fires up a totally different set of nerves, the parasympathetic nerves, and they tell the bladder muscle to contract and contract powerfully. And at the exact same time, it sends other signals that tell the external sphincter and the bladder neck to just relax and open up. You've got contraction and relaxation happening in perfect sync. It's amazing. And the engine that's driving that powerful squeeze, well, that's this right here, the detrusor muscle. In this close-up view, you can really see the thick, powerful bundles of smooth muscle that make up that bladder wall. This layer also has a more clinical name you should know, the muscularis propria. And that name, muscularis propria, is so important. Because you see, understanding this super precise anatomy isn't just for textbooks. It has huge implications for our health, especially when things go wrong. Just take a look at this quote from our source material. It says that the difference between cancer that's just in the lining and cancer that's gotten into the muscularis propria, well, that's the difference between superficial and invasive cancer. And that changes everything for a patient, their prognosis, their treatment, the whole plan. So when you look at this image again, you're not just looking at muscle cells anymore, are you? You're looking at a critical boundary line in medicine. For doctors, knowing if a disease has crossed from those inner layers into this deep muscle layer is absolutely fundamental. And this detailed map of the anatomy, it helps doctors solve a ton of other problems too. Like for an enlarged prostate, or BPH, doctors can design drugs that target specific muscle receptors right there at the bladder neck to help it relax. Or for bladder dysfunction, there are therapies like sacral neuromodulation that can directly tap into those nerve pathways we were just talking about to try and restore proper communication. See? The anatomy directly informs the treatment. So at the end of the day, it's pretty clear the bladder is so much more than a simple bag. It's an intelligent, dynamic, and super responsive organ that's in constant communication with our central nervous system. Its genius is really in its duality. On one hand, it's this incredibly resilient reservoir, all thanks to that special lining and those support structures. And on the other, it's a powerful pump, driven by that amazing detrusor muscle. And the whole thing is a smart system, just flawlessly governed by this sophisticated neural switchboard up in the brain. It really makes you wonder, doesn't it? What other parts of our bodies that we think of as simple are just hiding this incredible, complex, and intelligent design, just waiting for us to take a closer look?